Welcome back. Let's define a point estimator. When you have a sample statistic, it is used as a point estimator of a corresponding population parameter. So, for example, let's go back to the example of height. Let's say we are looking at all males in Sri Lanka, and one thing that we want to measure, let's say, is the mean height of males or average height of males in Sri Lanka. Now, so there is this true average or mean height for males in Sri Lanka, which we want to approximate. However, if you think about it, it's not quite possible to measure the height of every single person and then take the average. So rather, usually you take a sample. So let's say you take a sample of size 500. So you take a sample of 500 males and you measure their heights, and then you create a sample of measurements of height, and then you calculate the sample mean height. So the sample mean height then becomes an approximation for the population mean height. So sample mean height, that's a sample statistic, and it is a point estimator of the population mean height. So the sample mean is a point estimator of the population mean for whatever variable we are looking at. It doesn't have to be height. Now, the unbiased estimator. So a desirable property of a point estimator is that it is unbiased. It is an unbiased estimator. What that means is that the mean or the expectation of the sample statistic equals the associated population parameter. So in the example of height, we are using sample mean height as an estimator of the population mean height, and we want that to be so sample mean height is an unbiased estimator. What that means is that if I calculate the expectation of the sample mean height, then that's going to be equal to the population mean height. The expected value of the sample mean height is the population mean height. That's what it means to say that the sample mean height is an unbiased estimator for the population mean height. So in other words, the long run average of the point estimator is equal to the population parameter. And whether random sample is picked with or without replacement, the sample mean is an unbiased estimator of the population mean. So more precisely, what we are trying to say is that no matter whether the random sample is picked with or without replacement, the expected value of the sample mean x bar is equal to the population mean mu. And again, in terms of the height example, if x is denoting the variable height, then we are saying that the mean of the sample means, or average of the sample means, or the expected value of the sample means, is equal to the population mean height. Now, this is pretty easy to prove. The expected value x bar, and x bar is defined to be the sum x1 plus x2 plus dot 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 plus xn divided by n, where x1 through xn, these are the sample observations, and if you take the expected value of that, that's the same as n is fixed here, so that's the same as you take the expected value of x1 plus the expected value of x2 plus dot 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 plus expected value of xn divided by n. Now, the expected value of x1 has to be the population mean mu, and the same thing for all these expectations in the numerator. And the reason is, if you think about it, x1, so if you go back to the example of the height, x1 is what? It's, you pick a male in Sri Lanka randomly, and then you observe his height. So if you think about x1, well, the distribution of x1 is exactly the same as the population distribution. So the expected value of x1 should be mu, and so what you end up with is n times mu divided by n, which is exactly mu. So the expected value of x bar is mu, which means that the mean of the sample means is the population mean. So this proves that the sample mean is a unbiased estimator of the population mean. All right, so we're going to end the video with this proof. In the next video, we will be looking at the variance of the sampling distribution of the sample mean.